So let's start today's class then, and let me put it in the full screen mode. So I hope now you can see the things in full screen mode, right? Now it will not be a problem. So in the today's class, can you hear me? Are you able to hear me?
Yes, sir.
And the screen is like this full mode now, full screen visible.
Yes, sir, it is visible.
Okay. So let's start the discussion then. So today we will continue from where we have left in the last class. So last class we have completed the discussion about the MOSFET threshold voltage, and using that MOSFET threshold voltage, now we will derive the this drain current equation, and also we will understand the operation of the MOSFET. So both the things we will do. So we'll first understand like in what regions this MOSFET operates, and then for different regions what is the drain current equation which governs its behavior. So this is what the theme of probably today's, and if not possible, if we are not able to complete the things today, then in the next lecture. So the aim is like we'll complete this particular thing. We'll try to understand operation and the drain current equation. So what is not going on? So in the last class we saw this particular thing, that our device, when we consider it as a two terminal device, then as the gate voltage changes, the if the gate voltage is less than 0 or it is negative voltage, then for NMOS, for a case of NMOS, when your substrate is of P type, then the device works in accumulation region. And if the gate voltage is not negative but it is positive but a small value, then in that case the depletion region is formed. Okay, if the gate voltage is below threshold voltage, so then the depletion region is formed. Later on, when you keep on increasing the gate voltage and it goes beyond threshold voltage, that gives rise to the inversion region. Okay, so the in the depletion region the inversion region is formed then. So this is what we have seen. Now we will concentrate our whole attention in the inversion region. So in the inversion region itself, some other like the in some other modes the device will operate. So we'll see those, like in which regions it will operate then. In the inversion mode, if the device is in the inversion mode, then what happens? So let's say uh, so this is the theme of like today's class, you can say. So basically, up till now, what we have seen is like about the channel formation. So the diagram A. So in this slide, I'm talking about this diagram. So here you can see that up till now, what we have discussed is this channel formation. So during this channel formation, what is happening is the drain and source both are grounded, whereas we are only, the body is also grounded. So all there out of the four terminals, the three terminals are grounded, whereas the fourth terminal, which is the gate terminal, is only the voltage at the gate terminal is only we are changing only that voltage. Okay, so that voltage is only changed. So when this voltage is changed and it is like, let's say it is greater than threshold voltage, VGS is greater than threshold voltage. So once the VGS is greater than threshold voltage, then the channel is completely formed. The channel is uniform throughout the region, throughout the this under the gate region. So in this region, uh, starting from the source to the drain region, the channel is uniform throughout. Okay, so this is what we have seen up till now, and underneath you can see that the PN junction is also formed. Okay, some depletion region is also formed underneath the source and the drain region, and they are uniform. These regions are like uniform throughout. But now, if we this gate voltage is like, we will keep this gate voltage above threshold voltage, and now if we change the other voltages like the drain voltage, so will not change other voltages, like we will keep the source the source voltage and the body voltage same, but we will just change the drain voltage and we'll see the effect. And that what happens to the device. So in the diagram B, if you will see, So what happens here in the diagram B is, just give me a minute. So in the diagram B, what you do is, so in the diagram B, what happens is when we just uh, start our device, okay, so we have like applied some voltage. These diagrams are a little hazy, okay, because it was like difficult to draw them, so I've just copied it from the book, the images from the book, so they got little hazy. I must have like taken little care to make them this thing, but I'll try to explain them. If you have any doubt, you can ask me and I'll share the PPT, so you will not have any problem in understanding them. So you see here what we are doing, the other three voltages now, source voltage, gate voltage and the body voltage, we have kept constant. Source and body both are grounded, whereas the gate voltage is above the threshold voltage. Okay, so the inversion layer is underneath the gate region. Now we are just increasing this drain voltage, and that VD is, let's say, small. Okay, it's not a high value. We are keeping it small. So then in that case, what will happen to the device? So you see, actually what will happen now, if you just consider the difference, so we will consider this, that what will happen. So this is the second case, and in this case, the MOSFET will work as a resistance. So the linear region operation, we'll consider this as linear region. Then the third case, when you keep on increasing the voltage, then something happens. So this the channel doesn't remains uniform in the second case. It starts tapering in the towards the drain side. Okay, so the channel doesn't remain uniform. It gets narrow towards the drain side. And if you keep on increasing the drain voltage, and it becomes like equal to the VD set, what you called as VD set. So at that time, something happens which is called as the pinch off. So at that time, the channel is just about to extend. Okay, so the channel near the drain region becomes just like a point. Okay, so beyond that, if you increase your VD, so in the fourth diagram, if you'll see, if you keep on increasing the VD beyond VD set, then your this channel which was formed up till the drain, okay, now starts the length of the channel starts decreasing. Okay, so it moves towards the source side then. Okay, so this is what is happening into the when the device is like once the channel is formed into the inversion region. You have like three modes: linear region, and pinch off region, and the saturation region. Okay, so pinch off is like starting of the saturation. So while discussing the devices, we don't consider pinch off, but while deriving the drain current equation, we don't consider the pinch off case. There is no special equation for pinch off case, but will for understanding, like we will see that what happens at this instant and beyond this instant what happens. So that is what the things we need to see here, right? So let's move on and try to understand the things. Okay, these slides are like, okay. So let me first try to explain you this here in the diagram. Okay, I'll explain it in the next diagram. But before moving on to the explanation, to determine the drain current equation, we have to first understand that this particular thing, how to find the resistance for this channel. This we will require while deriving the drain current equation. So I'll give the explanation once again that what is happening actually in the linear region. Again, I'll move on to that. So one by one we will move on to this linear region, pinch off region, and the saturation region. So first diagram we have already seen in our last class, up till the last class. We'll discuss about the second, third, and fourth diagram in this particular this class, and probably the next class if we are not able to finish that. So to derive the drain current equation, we will require this resistance. So let's try to understand that how we can rewrite the resistance formula. So you already know that the resistance is like, you can easily, if you know the material, that what type of material you are using, so you can easily say that the resistance is equal to rho L by A. But that resistance rho L by A, we have to write it in terms of mobility, because we are using we are writing it for this R is equal to rho L by A is usually for conductors. Okay, but we have to write it for semiconductors, and here in the semiconductors, mobility plays the important role, right? So we have to write the formula in terms of mobility and the charge density, because usually we know about the charge density because the doping changes. If the doping changes, then the surface charge density also changes. Okay, so it's basically everything is happening on the surface, so we have to consider that whatever amount of charge present per unit area. So we'll try to rewrite the equation of the resistance in this terms. So let's try to see this particular thing, that how you can write this equation, and then we will move on to the explanation for the linear region. So you know this particular thing. I'll try to explain it in short because most of the things you already know. Just to have to see that how you rewrite the equation, manipulate the equations, and get the final equation. So you already know that from Ohm's law that V is equal to IR, right? And your I is equal to nothing but the basic definition of I is charge per unit time, isn't it? So that is what the equation is. So charge per unit time I have written. Now you also know from your this understanding from the basic electronics that the velocity of the charge carriers in a semiconductor is equal to nothing but the mobility of the charge carriers into the electric field, right? So V is equal to mu E, you also know, right? And V, velocity, is nothing but your some distance traveled divided by, the distance traveled in per unit time. So that is what the velocity is, velocity of charge carriers. So that is what I have written here. Now using this basic equations and the equation of like electric field, so I have not used the symbol negative of V by L, but I'm just trying to say, just mention you that how it will look like. Okay, so minus should also come here. So that minus if will come, obviously it will tell you that the charge carriers, this all is because of the electrons. So you see, E is equal to V by L. We already know it is dV by dL. dV by dx is equal to electric field, rate of change of potential. So that is what we have seen. Now we all know these equations. There is nothing new in this above 3-4 equations, right? Now if you just combine this 3 and 4 equation and rewrite this equation, so we can write this equation in this voltage in terms of this. Okay, so I have just used this particular things here, all of them. So I use this Q by T, okay, in this equation, and okay, not in this equation particularly, equation 5. I have used this voltage in terms of this electrical this velocity of the charge carriers. So if I just write E is equal to V by L, okay, and this V is equal to L by T, and write the equation in terms of voltage, so then I'll get this equation. Length square divided by mobility into time. So this is what I'll get. Now, as you know that this equation is also for the voltage and the first equation is also for the voltage. So now we can equate both these equations, right? So we equated both of them and we found that this particular I is also equal to Q by T. I have substituted here. So now you can write the equation in terms of resistance. So if you rewrite the equation in terms of resistance, then you find that the equation for the resistance is something like this. And then you keep on like because the time is like in the numerator and denominator, so they get cancelled out. So you get this equation. And in this equation, so this is like the equation which you got. But in the in case of this MOSFETs, we usually consider the surface charge density rather than the whole charge Q. If you have considered the this complete charge, then this equation is all okay, no problem. But if you are considering surface charge density, okay, which is like given in per meter square, so in that case you can rewrite the formula again. Okay, so in that case if you just rewrite, so if you are using Q as the surface charge density, then the whole charge, the complete charge in that area will be nothing but Q into W into L, right? So just instead of, because I am considering here Q as surface charge density, so if Q is the surface charge density, then you can rewrite the same equation, equation 6, in this form. Okay, and now this length also gets cancelled out because it is present in the numerator and denominator. So you get this equation, right? Length divided by mobility into surface charge density into width of the device. Is that okay? Is there any doubt in this particular thing? I don't think, because I have explained this clearly. And I've explained this clearly, tried, because this particular discussion is not given in your book, which you will follow. The SCANG. So this directly the formula, this resistance formula will be used. So probably you may find it difficult to understand and you will try to mug it up. So no need to just remember mug it up. There is like a small derivation. If you do, you can rewrite the equation in this form. Okay, so that is what the purpose of showing this particular thing, right? So any doubts in this discussion, in this resistance formula? No.
Sir, you are replacing meter square by like W into L, na sir? That means width into length.
Yes, area, no? It is like area.
Ah,
If you're talking about area,
yes,
so it
yes.
is width into length, it should be, right? Surface charge density, meter square. So meter square is area, surface charge density, no? Surface charge density, if I talk about. So if it is meter square, then it is obviously surface, so width into length will only come, right?
Okay, sir.
Okay, so let's move on. So this is the resistance. Now this resistance we will use wherever we will require in the derivation of drain current equation. So let's see. Now let's come back to the this particular thing, linear region. So let me listen. Just a minute. Huh? Okay. So you see here. Let's see this linear region once again, and like completely we will discuss these things here rather than there. It's better to discuss the things here. So you see here what I'm doing is again the same diagram, and the drain voltage, the source is like grounded, body is also grounded, gate voltage is little bit, I mean it's higher than threshold voltage, whereas the drain voltage now is not at zero but we are increasing, and the VDS is not very large, it is a small value. So then what will happen? Okay, so as I have told you earlier in the previous slide, that the channel doesn't remains uniform. It gets tapered toward the drain side, or it gets narrow towards the drain side. So why? Why it gets narrowed? Can you explain me this? Can you give me a little bit explanation for this thing? That why it gets narrow?
So, like particularly that the source is grounded and we are applying the positive voltage at drain side.
Hmm.
So drain is N plus. So like when we apply the positive voltage, then the depletion
Yes.
isn't there. It's
Hmm.
increasing
Hmm.
significantly.
Hmm.
So that's why like the charge density is more on the source side rather than on the drain side, because the depletion region is more in the drain side. So it is like eating up the channel particularly.
Very nice,
So
very nice. So you got
it,
it right. Okay, so this is what is happening actually. So if you just see, so what Abhinav was telling is very right. That what this is what is happening. So in simple terms, what he's saying is, if I try to explain you, so then what is happening? If you consider VGS at, let's say, VG at certain voltage, let's say 2 volt. Okay, so now you see the source is at 0 volts and drain is let's say at small volt at some small voltage, which is let's say 1 volt. Okay, so you just see them. So what will happen? The difference between the gate and the source, the voltage difference between the gate and the source and the gate and the drain will not be same. It will be different. The gate is at 2 volts, source is at 0 volts. So the difference between gate and source, this side will be 2 volts approximately. Whereas between the potential difference between in this half of the device will be approximately 1 volt. Okay, so the voltage difference is voltage between the two device these two halves will be different, and because of that, as the voltage is different between these regions, so the charge density is more towards the source region and it is less towards the drain region, because you are feeling like this region is feeling less potential difference. So that is what the reason is. Probably this is what you are saying now, Abhinav.
Yes, sir. Exactly, sir.
Okay. So this is what is happening here. So this is what the reason for this channel tapering, the narrow down of the channel towards the drain region. Now, if this is you consider, then you can also see that because of this voltage difference, the depletion region under the source and the drain region also gets affected. Okay, it gets narrowed down in this region, whereas because you are increasing more voltage here, so you see the reverse bias voltage will increase here in this case. So the drain region the area under the drain region will get more depleted compared to the area under the source region. Okay, so this is what also happens here. Now, if you just accept this particular explanation, then to derive the drain current equation, what we have to do is we will consider this channel region and what will happen into this channel region. So this is the channel region in this diagram. This is like the enlarged view is shown here, and considering this, we will derive this equation. So the point is, throughout this channel which we are seeing here, the voltage does not remain constant. It is changing continuously. At the source end, something else is there, and at the drain side, you are feeling some, the device is feeling some other voltage. Okay, so the voltage is continuously changing. So this you should keep in mind. So at a certain point, if I just consider, so I have to consider like what is the voltage at that the channel, what the channel is at particularly which volt, or at what voltage, so at that instant. So that is also we have to consider while writing the equation. Okay, so you see, let's try to see the equations which we should write to get the this particular drain current equation. So when your this is what I was telling you, that the channel VC is here channel voltage. So channel voltage is zero. Okay, is zero when near the source side. The channel is at zero voltage, let's say, and channel is at the drain side, it is VDS voltage. Okay, so whatever voltage you have applied, that voltage, let's say, and we will consider this particular length of the channel. Starting this point, we will consider y is equal to 0, let's say, and this is y is equal to L, because we will require this things to put in the integration limits. So that's why I'm telling you that at y is equal to 0, the voltage is 0, whereas at y is equal to L, the voltage will be VDS. Okay, so keep this in mind. Now, we have assumed that your gate to source voltage is greater than threshold voltage and your gate to drain voltage, okay, is also greater than threshold voltage, because then only the channel is forming. Let's say the example which I have taken, that here the source is at 0 volt and the drain was at 1 volt, and the oxide this gate voltage was at the gate terminal was at 2 volts. So in this case, let's say the threshold voltage of the device is 0.8 volts. Okay, so this particular condition is okay in this case. Okay, so this is what I mean, that the drain voltage, the potential which you are applying on the drain is greater than your threshold voltage. Okay, so then only you will get this channel, like tapered channel in this region and not the pinch off region. Okay, so this was it. And now you want to write, if you want to write the charge present, if you basically if you want to find the drain current, what the amount of current which is flowing between the source and the drain region, so what we have to do, we have to find the charge in this region first of all. Okay, so to find the charge in this particular region, what we do is we find the charge in a small region and then we integrate it throughout the limits, okay, between the source and the drain. So then we will be able to find the complete charge. So in this particular smaller region, okay, dy, okay, let's say small region if I take, and if I just try to find that what is the charge in this region, so how I can find? So we know that Q is equal to what? Q is equal to CV, right? So Q is equal to CV equation we are using here, and as the charge carriers are the negative charge carriers, it is NMOS, so we are using a minus sign here. So you can write the equation in this particular region, dy region, the amount of charge present in this region as this much. Q is equal to Q is equal to CV, and this voltage, if you will see here, is like having what? VGS minus VC minus VT. Not, not a single term, but there are multiple terms in this one. So this is actually the effective voltage which this particular region is feeling. Okay, so that is what the voltage is written here. Why VGS minus VC? Because this channel, as I have told you, this particular uh, element of this long length, okay, is facing this voltage, is at this voltage VC. So the effective voltage which this particular region dy, incremental region dy, will feel is this voltage VGS minus VT, because this is the effective voltage, okay, of the device. So VGS minus VT, and you have to subtract this channel voltage also, VC. Okay, so this is the charge present. Okay, now as I have also told you that we can use this charge to find the this current. So I is equal to Q by T, you know. So we will use this charge there. And if we write the equation, because we just know the voltages, so we have to write the equation in terms of voltage. So we know V is equal to IR. So our resistance we will require. So the formula for the resistance will be something like this, which we have to use. So you see, again, this formula, if you just compare it with what we have seen in the last slide, it is coming like that only. Okay, minus is there, as I have told you that minus should be there because of this charge density. And you see, this Qi is not the complete charge, it is the charge density which I am talking here. Okay, surface charge density, because this unit of Cox is farads per meter square. So this will have like coulombs per meter square unit. So that is why this charge here is in like per meter square. So if you use this charge per meter square here in this resistance formula, then if you compare the previous slides discussion, then you know that this is what this formula is written correctly. Okay, instead of length, the length here is dy. So that is what written here. Okay, W is okay of the width of the device. So this is the width of the device. So that is written here, width, and mu n is the mobility of the charge carriers. So here in this case, as the charge carriers are your electrons, so mu n is used. Okay, if you are deriving the equation for a PMOS, then you have to use a mu p here, right? And then this charge density. Okay, so this is what you get. So any doubt in this particular things? Equation of Qi and dr.
Sir, can you repeat, sir, this type of equation again?
Which one? What you
Yes, sir,
need to
QI, sir.
Qi. It is surface charge density. Q is equal to Cv. So capacitance I am taking this capacitance of oxide. Okay, because you see this is a sort of a parallel plate capacitor. So charge, whatever charge will come in this inversion layer is because of this capacitance phenomena. Okay, so that is what is happening. So that is why I have taken here Cox, capacitance per unit area, and then the voltage, which is like the effective voltage which is present on this this incremental region. Okay, this infinitely small region, this dy. Okay, and this is like a sort of complete area I am talking about. Complete volume, width into length. Okay, so this is what I am talking about. Is that okay?
Okay, sir.
Okay, and later on we'll revisit this after completing the discussion. We'll see this if you have any doubt. Once again, I'll try to clarify the doubts at that time. So drain current equation. Now you see, this is what the basic things we have accumulated, and now let's see that to write the drain current equation, to derive the drain current equation, what we have to do is just use this. So voltage is equal to, in this particular thing, if I want to find the change in voltage, so I can write this as dvc is equal to id into dr. So this the resistance of this infinitely small region, dr. So the drain current, this dvc, can be written if you just substitute the resistance formula here. So you get the formula this. And now, so this is important. So you see, if you want to, if this is the drain current equation for your infinitely small region, okay, then what will be the drain current region equation for the complete region? starting from the 0 up to the L. So to find that, what we do is we just integrate the things from 0 to L. So we write this equation, we got this equation for the infinitely small region. Now once we get this, then we will integrate it from 0 to L, right? So we are integrating it. So on integrating, we find that it is like 0 to L. So ID will be, because you see, just rewrite the equation. So you will find as ID into dy here, ID dy here. So ID dy. So this portion is written here and it is integrated from 0 to L. So dy is changing from 0 to L, right? Whereas simultaneously the gate voltage, this channel voltage is like at the when you are at y is equal to 0, the channel voltage is 0. Whereas at L, the voltage is becoming VDS. So that is why these limits are taken and you integrate them into this limits. And once you integrate them and just solve this, so you get the final equation for this thing. Okay, so this is what the equation is. ID is equal to mu n Cox W by L. Okay, half of mu n Cox W by L into, within the brackets you have twice of VGS minus VT0 into VDS minus VDS square, right? So this is what your drain current equation looks like in the linear region. Okay, so this is what the simple derivation, if you take this particular things. And this thing, mu and Cox, can be written in different ways. So if you write if you just take, because this will be constant, mobility of the charge carriers will be constant, and the oxide this oxide capacitance per unit area Cox will also be constant. So this is like termed as process transconductance parameter. Okay, so you can this is represented by k dash in the equation sometimes. Okay, so rather than writing this mu and Cox, we sometimes write it as k dash. So k dash is nothing but the process transconductance parameter. It's called as process transconductance parameter, and the value of this is mu and Cox. Whereas if you consider this k dash into W by L simultaneously in the equation together as a constant, because once you have fabricated the device, okay, then you cannot change its width and length. So the drain current will remain constant. So this particular thing will become constant in that case. Then you have the only thing to change is the drain to source voltage. Okay, so this also can be termed as a constant. So then this is called the device transconductance parameter K. Okay, is that okay? And then the same equation can be because this is the this popularly known equation. So the same equation which we have seen here or here can be written like this as well. ID is equal to mu n Cox W by L into VGS minus VT into VDS minus VDS square by 2. Right? So this equation you consider or this equation you consider. Both the equations are same only. Clear? So this equation, whenever like you will find that your device is working in the linear region. So use this equation. So whenever whenever your device is in a certain is used in a circuit, the very first thing which you have to do is find in which region it is operating, whether it is operating in the linear region or any other region. If it is operating in the linear region, then for that case use this equation. Okay, so this equation plays very important role, becomes very important in your further discussions. So whenever we will design anything, or we will further discussions, further lectures onwards, next lecture onwards, you will find this equation continuously. We will use this equation regularly. So be familiar with this equation. I know you are familiar, but if you are not, then just that's what the emphasis is. So now this happens. This is what the drain current equation becomes. Now once this is the drain current equation, then if you just try to plot this equation, then as you know that this equation is the equation of a parabola. This drain current equation what we have derived is the equation of parabola. So if you just plot this equation in terms of the drain current equation, drain current on the y-axis, whereas the this VDS on the y-axis, on the x-axis, sorry, VDS on the drain to source voltage on the x-axis, and the drain current on the y-axis. Okay, so you get this particular type of curve. Okay, so if your VGS is equal to, let's say, 3 volt constant, so then you will get this particular curve. If you increase the voltage, get to source voltage, then your voltage, this curve shifts upward. Why? Because the drain current will also increase. for a particular drain to source voltage, if you keep a drain to source voltage, let's say constant at certain point, and if you increase the gate to source voltage, so then what will happen? More number of charge carriers will be there. So because more number of charge carriers you can attract, so then the drain current will be higher. So that is what is happening here. So as you keep on increasing the gate to source voltage, so this particular graph, this type of graphs you will see later on when we will discuss the things, when we will derive the things for inverter, we will use this type of graphs. Okay, so this is the graph, and this graph particularly, as you can see, is it should behave like this. Okay, it should like if you use this particular equation throughout the whatever drain to source voltage you are increasing, if you keep on using this equation, so the curve should look like a parabola. But practically this doesn't happens. Okay, theoretically this is like practically this curve is followed up to this solid line. Okay, beyond this solid line this curve doesn't remains true. Okay, or that equations which we have derived doesn't remains true for the MOSFET. This the behavior of the MOSFET changes. So practically people have observed this. So first they have fabricated, and then they got the equation that the behavior of the device, and the behavior of the device is can be explained by that equation up till this in this the solid line, the region in which you can see the solid line, and up till that region only. Beyond that region, if you try to guess the device current by the help of those equations, then you fail. Okay, so the model fails. So now what happens? So beyond this region, what happens actually? So let's try to see this. So in the linear region, the device was something like that. So when your VD was small, so that is what is happening. But now when your VD becomes something like which you call as saturation voltage, reaches up to that voltage, VD sat. So what happens? And this voltage is exactly equal to, let's say, your threshold voltage. So if your excuse me, so what I'm saying is if your VGS, okay, this gate to source is now 2 volts. Okay, so gate is at 2 volts, source is at 0 volts, so this is 2 volts. Okay, and this particular voltage V gate to drain, okay, it should this difference should be exactly equal to the threshold voltage. Okay, I'm not saying that this VD should be equal to threshold voltage. This difference should be exactly equal to the threshold voltage. If this difference is exactly equal to the threshold voltage, that is here in this case, if you consider this gate to be equal to this threshold voltage equal to be 0.8 volts. So then this should be equal to how much? 1.2 volts. So if VD is equal to becomes 1.2 volts. Okay, just wait a minute. Okay, I'll bring my charger adapter. Just wait a minute. So can you hear me? I lost the connection, I think.